Thanks everyone. Thanks for coming to this year's PyData London. Happy to be here again. This is a brand new tutorial. I've given a few here at various PyDatas, and I'm excited to give you some new content. So the setup here, if you want to follow along, is on my GitHub, ts_PyData_London_2025. You can set it up with Conda or Pixie. We like Pixie these days, apparently, so I set it up with Pixie too. You don't have to do any of this. You can just be lulled to sleep with my dulcet Canadian tones. If you'd rather do that, follow along. It's all going to be Jupyter Notebook driven. And here, I wonder if, now do we prefer light or dark? Who likes dark? Who prefers light? All right, we're sticking with light. Boom, perfect. Yeah, I don't blame you. I think this is better. All right, so this was advertised as an introductory tutorial, so I'm going to follow through on that. So I'm not going to make any assumptions about whether these, your time series econometricians or already Bayesian statisticians. So we're going to ease into this with a little bit of time series background and a little bit of PyMC background, but not too much. And then focus heavily on implementing time series models in PyMC, which will take up most of the content, I think. And I'm still bad at timing 90-minute talks, even though I've done a lot of them. So I think I've got more material here than we need, but that's fine. Some of the advanced stuff at the end, it's fine. You can do it yourself, or I think it'll be the Gaussian process stuff that we might not finish. And me and Alex and Dora did a whole PyData New York on Gaussian processes, so you can watch that if you really want to. So it should be good. I'm excited about this. How many of you have done time series analyses before? Quite a few. Okay, so we could move quickly through this first part. How many of you have built PyMC models before? Bayesian models? Okay, fewer. Okay, so maybe spend more time on the PyMC, less time on time series 101. That's fine. We'll move it along. So if there are questions during this, please raise your hand and interact rather than just me talking the whole time. So welcome questions. So let's go. So just a quick justification. Why are we interested in time series? Well, you're all here, so I think you're interested. The world's dynamic. Things we care about change over time, right? And so we either are interested in looking back in time and figuring out what happened to get us to where we are now, or probably more commonly, we're interested in the future and what it might bring. And so time series models help us plan, assess risk, help us make better decisions, hopefully, if we do it correctly and we use that information. And so time series analysis is a very old topic, and Bayesian perhaps a little bit newer, right? And the Bayesian models aren't that different from the non-Bayesian ones. You're just sort of injecting a little bit of a different statistical paradigm into things. So we'll build the same sorts of models that you've built before: autoregressive models, moving average models, structural models. It's not different in that sense. But what it allows us to do is to sometimes be more flexible. We're in the age of big data, but often we have small data in time series, things that are only collected once at a point of time. And so dealing with small sample size, it can be difficult. And so we at least want to be able to put proper uncertainty bounds on things that are derived from small samples. And along with that, we often have information that's not in our data that we want to include in the model. And Bayesians call this prior information, and we have a principled way of incorporating that into our analysis. But the big one is uncertainty quantification, right? We don't just want a prediction into the future. We want a whole bunch of predictions into the future, and we want to see what the most likely ones are. And so turning time series modeling into a probabilistic exercise is really helpful. So that's why we're here. That's what we're going to do. Just load a few libraries here. So key character, the things that we are trying to model, you can break down time series. Again, I'm sure a lot of you have done this already. We'll do it here below, but we sometimes see trends, either linear or nonlinear trends, so how things kind of move over long time periods, not talking about short-term oscillations, but longer-term changes that we want to include. Time series are often seasonal, so these are fixed intervals oscillating over fixed intervals in kind of a predictable fashion that you aren't necessarily interested in, but we have to account for. And then relatedly, cyclical patterns are periodic as well, but perhaps not as regular, right? So business cycles, ecological cycles like El Nino. We'll look into some small mammal population ecology data sets here today that are cyclical, those sorts of things. And then, we'll pull everything else into kind of irregular stuff, noise, effects of days of the week, holidays, pandemics, things like that. All of this we want to be able to include at different points in time. And then the key thing, why can't you just use regular statistical modeling on time series? The big reason is temporal dependence, right? So statistical analyses often make assumptions like independently and identically distributed, the IID. That goes out the window with time series, right? So nothing's independent. Sometimes they're independent, but usually they're sequentially correlated with one another, right? So we've got autocorrelation often in these that we got to account for. And fine, you can throw a regression at that, and we will do that here as a first example in a second. But you'll sacrifice some of your assumptions, particularly about how certain you are about your estimates, are going to be off if you don't take care of that. So they're not independent usually, and they're often not identically distributed. So the variance can change over time. Things might be more variable in the summer than they are in the winter, that sort of thing, or variation expands over time as sort of the system gets larger. That's a frequent thing as well. So we have these, lags over which things are autocorrelated. So this sort of thing. So here's just a simple autoregressive time series, and one lag autoregressive, and that autocorrelation extends beyond one time period. Takes a few lags to go away before things are kind of independent. And then, another important concept is stationarity. It's an assumption that you'll make sometimes about how time series will evolve over time. So that one, stationarity means that your mean isn't kind of wiggling around all over the place. Your variation is relatively stable. A lot of our methodologies will assume stationarity. And so if they're not, you often have to do transformations to make that happen, or explicitly model that lack of stationarity directly. So just to give you an idea, there's sort of a stationary series. Depends on what you mean by stationary. Fully stationary would, the variance would probably be more stable than that, but the mean is more or less stationary in this first time series, whereas the second, it clearly isn't. Okay, so again, I'm not going to spend a lot of time on the background in time series because I think most of you know this stuff. So some interesting data sets. I try to change up my data sets in various tutorials so they don't get boring, and so I'm going to use one. I often also steal things from Andrew Gelman, so I'm going to do that again today. This is a fun data set. This is a births data set, just birth counts in the United States daily for 2 decades. And in fact, it adorns the cover of his most recent edition of Bayesian data analysis. So it's a good one because it contains a lot of these concepts that I just covered. So we can import that here. So yeah, 228 months spanning from 1970 to 1988, lots of births, and it shows a lot of kind of periodic behavior, trend behavior. So we can see things oscillating week to week, month to month. There tend to be more births in the summer than in the winter. Lots of births in September, August and September particularly. And then in the United States, the birth rate dipped a bit in the 70s and then has been increasing ever since. And the variability has stayed more or less the same. So we have sort of stationary variation, but not mean here. Okay, and again, not being Bayesian at all yet, this all can be decomposed relatively simply to these various components. So, you know, there's the original data. You could look at the underlying trend by smoothing out all of the periodicities, and then just look at the seasonality, and then what's left over after you account for the trend and the seasonality. And so we'll build a model a little bit later that does a good job of taking care of each of these things, all in a single model. And then autocorrelation, you know, just looking at the various time series, you can kind of predict what the autocorrelation is going to look like. You can see the annual lag there and the dip, and the things are more perfectly correlated from sort of year over year, but even that year over year autocorrelation is declining over time. So lots of patterns within that. A little bit of preprocessing. So preprocessing is important, as I said before, in time series to take care of things like lack of stationarity. It's often useful to, more useful for computational reasons. For example, in this, if you're modeling this time series data set that takes place over multiple years, and you use year directly as an input variable, and you include a quadratic term that we'll do in a second, in 1970 squared is a very large number, and if you put a coefficient on that, it's going to be very, very, very small. So you can avoid numerical issues by doing things like standardization, min-max scaling, and so forth. So things that are digestible by humans aren't always the same scales that are easily digestible by models. So we'll be doing a fair bit of pre-processing here. And I gave you a few examples of that here. Okay. All right. Yeah. Any questions on the basics? A few references here if you need more. Let's move on to Bayes now. Okay, so really quick introduction to both Bayesian inference in general, for those of you who have never seen it before or have only ever just heard of it, and then a little introduction to the PyMC API, which will be briefer than I like, but I'll be exposing it to you over the next hour and 15 minutes, so you'll get even more exposure that way. So what is Bayes? Well, you can think of statistics as falling into at least 2 paradigms. And like I said before, you know, Bayesian time series analysis isn't a whole different set of models as the classical ones. It's just a different way of looking at them and implementing them. So similarly, you know, Bayesian statistics is not just a bunch of different methods, right? So you can do classical regression, you can do Bayesian regression, you can do a classical analysis of variance, you can do a Bayesian one. They're more more so, it's a different way of looking at the world. And so if you're a frequentist like this gentleman was, Ronald Fisher, you are saying that your data are random quantities, right? So you're modeling these as random outcomes from a stochastic system. Every time you go out and observe the world, you'll observe slightly different values. And your parameters, your unknown quantities that you're interested in, your rates, your coefficients of regression parameters, all that stuff, are fixed quantities. And so what we do is we condition on the fixed things and try to model the random things. And so this expression here describes that. It describes what's the probability of having observed this data given these parameters. And then you go out as a good frequentist and you come up with an estimator for your estimand, which is your unknown parameters. Put a little hat on the parameter, means estimated parameters. So you want estimates of your parameters, and you do that with estimators, right? So every new problem, you got to go out and come up with new estimators for things. So it takes a lot of skill to be a good frequentist. And you can I sort of tout Bayesian inference as being all about uncertainty quantification. It's not like you can't quantify uncertainty as a frequentist. They do a fine job of it. It's just, it's a little bit harder to interpret, right? You get things like confidence intervals, which isn't quite what you think it is some of the time. It's not the probability of the true value being between these two endpoints is 95%. That's not it. It's, if you went out and repeated your experiments an infinite number of times, 95% of the intervals would contain the true value. And that's a slightly different thing. Sometimes they're more or less the same, but it's not the same. If you're a Bayesian, like the only known Bayesian picture in the world, Thomas Bayes, you could put Simone Laplace up there too. You look at the world exactly the other way around, right? Your data, when you collect your data and you come back tomorrow and look in the fridge or wherever you keep it, it's the same, right? It hasn't changed. So your data are fixed. It used to be random, but they're not random anymore. So we're going to condition on those, and we're going to say that the parameters are random, except they're not, right? Well, sometimes they are. If they're time series, they're definitely random. They're going to change, but we're not saying that they're ever changing. We're saying that we're going to treat it as a value from a probability distribution, and that probability distribution will quantify the uncertainty. So it's going to be a randomness in terms of knowledge, in terms of certainty, not randomness in terms of, things, the data changing. So fixed, random parameters, fixed data, and hence we're now worried about what's the most likely value, what's the most probable value of an underlying quantity of interest, given that we've observed these data. So it's a little bit more of a direct statement about the things we care about. We don't actually care about our data. It seems like we do, but we don't. We wouldn't collect any data if we didn't have to. We're collecting data because we're interested in something that we can't see, usually. So, and so this allows us to make more direct claims about the value of that parameter. We can say that there's a 95% chance that the value is between this and that, and that can be easier to interpret for some people. And we're not worried about p-values and hypothesis tests and other things that are complicated. All right? And the other advantage that Bayes has is that there aren't an infinite number of estimators. There aren't bespoke estimators for every problem. There's one estimator, and this is it. And the only problem with having a light theme is that you can't have yellow text, but I think it looks better on your screen than mine. So this is the only estimator in Bayes, so we can learn it. You might have seen this before, but so the thing that I just wrote down, that's the probability of our parameters given our data. So our parameters here are theta. If you're lucky, there's only one of them, but it's usually a vector or a matrix or a vector of matrices or something bigger than that. And we're conditioning on our data. And how do we get that? That's the thing we want. Well, we use Bayes' formula to do that. Bayes' formula is just a tool for learning about parameters from data. And so we start out with no data. So our prior probability is the probability of theta. What does that mean? It means what do we know about our unknowns before we've looked at any data. And by before we've looked at any data, I mean my data, not all the data that's ever been collected. So there is often information from other places that you would want to put in your prior distribution. Sometimes not. Sometimes you'd be ignorant, but it doesn't have to be. And then we add our data. So probability of y given theta, that's the thing that the frequentists like, right? That's the sampling distribution. That's data our random world. But we still use it in Bayes, but we use that to update. We use that to inject that information and update it to give us our posterior probability. Okay? And then the thing that we don't mention is this denominator here, which is a real pain. This is the normalizing constant. From a practical standpoint, it's a normalizing constant, and that's why we worry about it as statisticians. This is what guarantees that our posterior probability is also a probability. So our priors are probability distributions. We want our posterior distributions to also be probability distributions, so we have to normalize it so that they integrate to 1, right? It's also what they call the model evidence. It's the numerator integrated over all of theta. Do I have this down here? I don't think so. And so it's hard to calculate. And so that's what makes Bayesian inference really hard. That's why we need packages like STAN and TensorFlow probability and PyMC so that we can do this numeric computationally. It's really, you can't do multidimensional integration at all, right? For more than a couple of parameters. Okay? So the whole learning process then is kind of turning the Bayesian crank. You start out with your priors, and you observe some, not just observe some data, but you actually add it to your model as a likelihood function, and then you update it to posterior. And then in practice, everybody says this is the cool thing you do with Bayes. Hardly anybody does it. You can use your posteriors from your last study and use them as priors for the next one. Sometimes people do this, but not always. It's hard to do too. Okay, so how do you do this, right? So depending on who you are, different parts of this whole process are easy and some are hard, right? If you're a statistician, writing it down all your entire system as a mathematical statistical model is easy. If you come from computer science and machine learning, it might be the hard part. But if you're a theoretical statistician, MCMC sampling might be hard. Calculating the prior might be the hard thing. But if you're a computer scientist, it's easy, particularly if you're like a physicist or something. So the first hard part is encoding everything as priors, right? How do you come up with a prior? Sometimes you just make it up. Sometimes you use priors somebody else has used, which isn't a great choice, but that's how these sort of statistical traditions happen. Sometimes you have information, right? You have prior information. Like in the example here, let's say we know birth rates range between 10 to 20 per 1,000 people. Well, if that's the case, you might make a normal distribution with the mean in between that and a standard deviation of about 2. That's a good prior. And that encodes that knowledge. There's a whole companion package to PyMC called prelis that I don't think I used today that's all about eliciting priors. So if you're really interested in that, look at prelis. You can have what's called weakly informative prior that says, well, I don't know much about this, but I know that, if I'm doing genetic experiments and measuring fly wing widths, they're not going to be, 1 times 10 to the 6th meters. So we can constrain it to something that's kind of biologically realistic. So weakly informative says I'm going to mostly plead ignorance, but I'm going to put bounds on it. It's going to be reasonable. I'm not going to cause numerical problems or computational problems by making things that are way too sparse. And then there's pure non-informative priors. Some people say, I just want to let the data speak for itself. And just, everything is game before you look at the data, which can work sometimes, but can get you into trouble a lot of the time. Okay, so how do you choose this? Well, starting with weakly informative priors is always a good place to start. If you don't know, just make sure that it's wide enough to include all plausible values and then start from there. Use domain knowledge. That's even better. If you are a geneticist and you're building a genetic model, use what you know to create your priors. But the good thing is that if you make a mistake, you can always go back and change them. It's one of these frequentist things too, like you're not allowed to look at your data before you run your test, and you can only run your test once. You can't do it more than once because the design of the whole experiment matters. In Bayes, none of that matters, right? So if your priors are causing problems, you can go back and change them, right? Which sounds kind of weird and non-scientific and arbitrary, but you're being explicit about it. You're not hiding it, right? It's like, these are my priors. If you don't like them, put your own priors on there and see what happens. And sometimes you change the priors. Sometimes you do each of these, and it doesn't matter. You get the same result. Often, if you have enough data, none of this matters. So don't worry about it. Don't wring your hands about it too much. But the point is, A, you always check to see if your priors matter. And B, if they do matter, you think harder about it and make good choices and change them if they're the wrong ones. No big deal. Similar for likelihoods. Likelihoods, you're trying to come up with kind of your data generating process, right? So are things continuous, or are they count? Births are counts, right? You can use continuous likelihoods for that, but sometimes counting discrete distributions like a Poisson or a binomial, if there's an upper bound. See, births, there's no sort of natural upper bound to births, so binomial's not a good distribution to use. But I used to work in baseball, so if you're trying to predict how well a baseball hitter hits, you're modeling. He came up to the plate 624 times and got 150 hits. So that's a binomial distribution. So your data generating process kind of naturally informs what your likelihoods should be. So how do you choose your likelihoods? Match the distribution to the characteristics of the data. Are they bounded at, are they things you measure so they can't be negative, or are they defined on the real line, and so on. Use robust alternatives when it makes sense to do that. If there are a lot of outliers in your data, you might want to look at a student t distribution instead of a normal distribution. Or if your counts are all over the place, a negative binomial distribution is kind of like a Poisson, but it's got an over-dispersion parameter that lets the variance and the mean be different. And yeah, let the data generating process guide you. Kind of think about how the data got there, and that usually is helpful. Okay, so load the libraries, hooray. Let's go back to the births data set like we did before. And let's work a little bit. I'm just gonna fit a kind of a crappy model just to give you an idea now about how PyMC works. Give you a little bit of idea about the API. So again, the concise version of the Bayesian workflow is that you define your model. So you write it in Python usually, or in PyMC and Stan, and you write down your likelihoods and your priors. And so the cool thing is that we don't have to worry about the normalizing constant and Bayes formula. All we need is the joint distribution. So everything in your model has to have a distribution. Your likelihood, your prior, missing data, predictions, anything that you want to be included has to have a distribution around it. So we'll start with a polynomial regression model. So we'll just fit a polynomial, because remember we saw the births and it kind of had a little quadratic thingy going. And we'll kind of ignore the oscillations for the time being. Let's see if we can get that trend. So we'll fit a polynomial regression. So this is it. It's just a mean, a linear coefficient, a quadratic coefficient, and that generates a prediction. And then there's this error term, and that error term is going to be given a normal distribution with a standard deviation of sigma. So specify our prior. So what are our priors? What are our likelihoods? Well, our likelihood, I've just told you, is normal. I'm not giving you a choice, even though I just said births is probably better modeled with a Poisson. But forget I said that. We're going to do normal for now. Again, we can always go back and change it. There's nothing wrong with building the wrong model to begin with. In fact, I recommend it. Build the simplest, stupidest model first, and then make it better over time. So our priors are going to be the intercept, 2 regression coefficients, and a error standard deviation. So four priors we need, and 1 likelihood. And so this is what a PyMC model looks like. Let me get rid of my search here. So everything happens inside of this context manager. So with statement in Python is a context manager. It usually is used for things like managing network connections and things like that. Here we're going to use it to manage models. So I instantiate a model. I'm giving it a bunch of coordinates that I'll tell you a little bit more about later, but it's just a set of labels essentially. So time, it's going to be a time index. My coefficients are going to be linear and quadratic. I'm going to call it polymodel. And so our priors are going to be here. So here's a normal distribution for mu, the mean, just a standard normal in this case. And then my beta is similarly a standard normal. And then notice I give it dims here. So I could also put shape equals 2, but then they would have integer labels 0 and 1, and I gave them nice, intelligible labels, linear and quadratic. So this is going to be a scalar normal. This is going to be a vector valued normal. Okay. And then just doing a little data manipulation. So I need quadratic. So I take my data, my input data, and I also square it and stack them together. I'm probably not doing this the best way, but it's for teaching. And then so these are kind of random quantities, and now I need sort of a non-random quantity. I just need a transformation, and my transformation here is just my expected value for my regression. So it's mu plus the vector matrix operation and multiplying my data by the regression coefficients. And so deterministic is just a wrapper, a PyMC wrapper for transformations, essentially. So these are deterministic because it doesn't add any additional stochasticity to my model, right? The things going into it are stochastic, but I'm not adding any more, so we call it deterministic. We're not sure if that's the best name. And then sigma. So sigma is a standard deviation. So thinking about the prior there, I don't want to give it a normal prior because we don't like negative variances. So we're going to give it a half normal. There's, again, a bunch of different choices, but I'll just, for now, make it easy, half normal. So we truncate it at 0. And then my likelihood is also a normal. It's normals all the way down on this model. So it's normal, but now the mu, this isn't a prior because the mu is our hyperparameters. So we're building a model for our data. The thing that makes it a likelihood, though, is that we pass it our data. So observed, we're saying that it's observed. And so what this essentially does is kind of pins this node in our model to these values. And it's got dimensions time, because there's however many years. I think I'm just looking at the year data here. Okay? And then I fit the model with a magic function called pm.sample. And it's magic because it abstracts away all the nasty calculations and approximations of priors. This is all you have to know. I don't even have to do any of this. I can just delete all of this. I can just do that. Oops. Okay, and oh, I forgot to run the cells above it. Ooh, did I not have time index here? Oh, I must be missing a cell. All right. A little bit of surgery here, sorry. I'm pretty sure I ran this thing before did I delete something accidentally?
I made an issue on your.
Did you? I ran it like last night. Damn it. Okay, thank you. Yeah, they are, aren't they? I tried to switch to Marimo, but they don't like Python models or PyMC models yet. Dang it. It was here yesterday, so it's in there somewhere. Time normalized. It's not here. Well, that will ruin things. I'm not even using cursor. I could have just asked cursor to create them for me. All right. Did you say you found them somewhere else?
If you go to the issues section of your GitHub, I put the lines that I think need to go.
Dang it, thank you. Issues. Thank you. You're a lifesaver. Okay. Ah, you're a hero. Okay. All right, so gives you a bunch of feedback about what it's doing. Again, you don't have to worry about it. So I'm not going to talk at all about Markov chain Monte Carlo. So this is the method we're using to fit models. We're gonna black box the whole thing, other than to look at some diagnostics. So we fit the model, and we have a bunch of samples from the posterior distribution, or an approximation to it that's supposed to be good. And so now we have estimates for all of this stuff. We can always look at our model, so that's the structure of our model, just to check and make sure. It's a good way to check our models. And we can see that, here's our posterior distributions of each of the parameters, and that's our terrible fit to the data, right? So we've taken care of, a part of it, but not all of it. So that's kind of how we fit PyMC models. There are a bunch of diagnostics that we want to do when we're fitting models with MCMC. The first kind of step in the check is to make sure that things converged. And the first thing you can do is just look at this run and see if there are any warnings, and there are none. So things went relatively well. But there are a bunch of diagnostics. There's a thing called an R-hat statistic that measures convergence, and if these values are near 1, we're good. Effective sample size. When things are highly autocorrelated, your effective sample size goes down, so you don't have as much information in consecutive samples as you would otherwise. So you want your sample size to be high because you're trying to estimate things with data, with samples. And then weird things called energy diagnostics that I will show you in a second. So this is using, the MCMC algorithm we're using is a gradient-based one, which is why we have to use PyTensor on the back end to do automatic differentiation. It walks around the gradient of the posterior distribution. And so we can actually use that gradient information to give us hints as to whether things sampled well. And so you'll get these two distributions of energy. It models a Hamiltonian system, position and momentum. And if you compare the marginal energy to the transition energy from each step, they want to overlap. So all you have to know from an applied sense is, do these distributions overlap? And this is a good enough overlap. So you'll know if it's bad, like they'll be in two different places sometimes. So just some checks. And then the other check we do is kind of a validity check. So we did, so this is called posterior predictive checking. So we fit our model, and once we fit our model, we can use it to generate simulated data. We have a data generating mechanism through this likelihood. And so we generate a whole bunch of simulated data sets, and we compare it to the data that we actually observed, and we ask, well, does the data look like it could have come from this model? And so the black line is the data. The blue lines are a bunch of simulated ones, and it's not great, right? It deviates in key places. It's not horrible. You'll see much worse than this, but it's pretty obvious that it's not an amazing fit just by looking at that curve, right? But this wasn't meant to be a good fit. I did this on purpose. Okay, so I just went through the Bayesian workflow. In the interest of time, I'll speed through this part a little bit, but it's exactly what I said, right? You write your model down. I didn't do that here, but you can do prior predictive checking too. You can simulate from the data, or from the model, without fitting your model, and you can see what you specified all these priors using God knows what principles, randomly read it in a book. What does this mean? What does this imply about my model? Before it looks at any data, you can do that. That's a good way to do model checking as well. And then, so then you fit the model, do convergence diagnostics, which includes posterior predictive checking. And then once you're happy with all that, then you can do inference and decision making. I'm not happy with this model, right? So I'm going to stop and not do inference and decision making. I'm not going to write up my report. I'm going to go back now and make my model better. Okay? Any questions about any of that? Again, that's fastest I've ever covered PyMC, but hopefully it's enough for you to understand the model fitting that we'll be doing here. And there's lots of resources for you otherwise. So I'm going to start with simple models and then work our way up to more complex ones if there's time. And I'm going to switch data sets. So switch from human births in the US to ground squirrel births in Canada. So these are ground squirrel, that's an Arctic ground squirrel. We usually use the snowshoe hare data set, right? This hare and lynx thing you often see as an example. These are Arctic ground squirrels. They live in the same place. I actually, as an undergraduate at the University of British Columbia, spent a summer working in the Yukon on this study, the Kluane study, catching birds, putting rings on them, and catching ground squirrels and putting tags on their ears, that sort of thing. So I collected some of this. Actually, the data I collected is after this period. So here's the ground squirrel data. And it's sort of like the hare data. So the snowshoe hare oscillates really heavily, and it's related to the predators' dynamics as well. So it's a really good time series analysis subject. The ground squirrels are less closely tied to that cycle, so you can see cycles here, but they're not as, and this is spring and summer too, so. But I think I'm just gonna look in the summer here. So I wanna model this, right? I wanna look at, and what I'm modeling here actually are densities, not counts. So these are densities that have been estimated using mark recapture analysis. So our data is actually a derived quantity, which is a little weird. So one of the simpler time series models is random walk models. And random walk models essentially draw a deviate that's usually normal, and you add it to your current value, and you get a new value. And so we call it kind of a non-parametric model because you can't see any clear parameters here really. There's actually lots of parameters. They're just, they scale with the size of the data. The more data you have, the more random walk pieces you'll have, and it grows and shrinks with your data. A Gaussian random walk is where this epsilon is normally distributed. And it's stationary, mean stationary usually, but not variation stationary in the sense that it'll typically grow over time because the variation of a particular observation in the future is going to be t times sigma, as we'll see in a second. The other approach I'm going to use in this model, make it slightly more interesting, is I'm going to use state space modeling. So I'm going to separate, excuse me, the latent, I'm going to call it a latent unknown state because I'm using densities here that have been estimated from a model from the observed state, from my data. Right, so there's a state equation, so I'm interested in some true latent value that's moving through time, what the true density is, versus the observed density or the inferred density. And so I've got a sigma here that describes the process of the underlying, the biological process, and then the observation process. And so we're going to try to tease those apart. So this time series, in some sense, is all about teasing apart different sources of variation, right? And we're going to start here. So this just isolates the summer data. And so here's my Bayesian random walk model. And we have distributions for time series analysis built into PyMC. Random walks are actually easy to do without that. You just take a whole bunch of normal 0 sigmas and just cumulative sum them, and that's your random. That's essentially what's happening under the hood here. And so you can give it a drift parameter. I didn't see much driftiness going on here, so I left it at 0. but you do supply the sigma walk. You give it an initial distribution, and that initial distribution isn't actually a PyMC object. When you use the dist method, you're actually stripping out all the PyMC random variable stuff, and that's just a raw normal distribution that you can sample from. It's got no label, it's got no association directly with them. It's not gonna be a node in the graph. And that's an initial distribution that this will change. And then my random walk here, excuse me. Sorry, let's start with the likelihood. I'm gonna use a log normal here because you can't have negative densities, right? So this is my way of dealing with positive measurements. And so I'm gonna take the random walk in the nominal scale, and then I will take the inverse log of it and pass it to the likelihood, okay? And I'm gonna sample from it. And look, I got a bunch of errors here that I'm kind of gonna ignore for now. But these are, for one thing, my progress bar turned red. That's never a good thing. And then I got these things called divergences, which have to do with the fact that this Hamiltonian physics model went off the rails. And it's like the satellite losing orbit and spinning off into space. That's what happened to 17 of my samples. And then the R hat statistic is larger than 1.01. So these are all hints that MCMC hasn't converged. So I can go back, excuse me, I'm not sure what's wrong with my voice. I'll give it more tuning steps here. And it seems to have helped for one of them, but not all of them. But it's okay. For what we're doing here, it's going to be fine. Trust me. It's informative to look at the relative variances, so the signal versus noise, if you want to call it that. So the random walk standard deviation is bigger than the observation error. And then we can sample from, so we're going to do what's called retrodiction now. We're going to try to back calculate what the densities actually were. So estimate the true underlying series of densities are. And it looks like that. And so the green line, you notice the green line doesn't go through the observations. So it kind of looks like it smoothed things a little bit. So it attributed some of that variability to noise and not to the actual population dynamics. And so there's two intervals here. One is, I think, can you see two? On mine there's two. All right, so the interval you can see is the 95% highest density at interval, which is the smallest 95% interval that you can get. So it's usually the central one. So that's the uncertainty in that green line. And then there's another lighter green that comes out to about here, and that's the prediction interval. So thank you, I've got a liquid here. It's just, thank you. And that adds sampling variation as well. So if I had to do prediction, so the dark green interval is the uncertainty in the green line. The light green interval that you can't see is the uncertainty in the red dots, essentially. Okay, and then so forecasting then. So something we want to do with any time series model is forecast. And so I might want to forecast ahead, 10 years, and it's easy to do with a random walk, right? All you need is that standard deviation and the last location of the estimate, and it kind of looks like that. And so typically it would be, a big, what? No, I'm good, thank you. It would go out in both directions, but we're bounded at 0 here. This is a log normal. So, and it's not a particularly useful model, right? It's not just going to go in a straight line forever. Come on. But it's a very simple model, but it is very honest about how uncertain it is. It's honest about its crappiness. Okay. So let's refine this a little bit and move to an autoregressive model. An autoregressive model is actually just a generalization of the random walk, where rather than just taking the last observation, it's going to be a function of the last observation. So we have this coefficient. So when phi here is 1, then you'll notice it becomes a random walk. When phi is 0, it becomes white noise, right? It's just independent. And so you should maybe always use autoregressive models, because in the extreme, you can always estimate it to be a random walk if you want to. So the only difference here is that it's got that coefficient. And so we have pm.ar. And the cool thing about that is that you pass in a row. Sorry, I used phi up here, and I'm using rho down here. I'm passing in the coefficient that is scalar here, and it knows that it's an AR1. So I'm only modeling one lag here. It's only related to the last observation. Everything else looks very similar to the random walk, because it is. In fact, the rest of the model is exactly the same. So now I'm going to hit the random walk, and it's also similarly bad at sampling, but we're not going to worry about it. And it also looks very similar, which maybe isn't surprising, right? Because it's just it'll just have a different coefficient than 1. And we can generalize these to multiple lags, right? Which is sometimes appropriate. AR1 is what we call Markovian, right? History doesn't matter. All that matters is the current state to predict the future state. Well, sometimes history does matter. And actually, things like ground squirrels, it does, right? Because the population next year can depend on things that happened a few years ago, like if mama squirrel was starved when she was a baby, she's not going to have as many kids when she's reproductive in the next year, things like that. So history can matter, or various environmental responses that take more than a year. So this is exactly the same model, except for this. So I put 2 lags in here. So now rho is of length 2, and so this will automatically be an AR2 model. So it's really nice, really nice. It's nice to have a high-level interface. You don't have to rewrite everything. Still samples poorly, check. Yeah, you can see the estimates. These are the distributions of rho. So look, the first one is positive, mostly, and the second one is negative, mostly. Could be 0. There could be no second lag. We're not. See, we have uncertainty. We don't know, right? It's probably a little negative, you would say, but there could be none. It could be positive. We don't know. It's a small sample size. Okay. So let's generate predictions with this, but now we're going to use PyMC machinery to do this. And this is a cool way to generate forecasts with these models. Here's what we're going to do. Listen closely, because it's a little confusing. So what we're going to do is we're going to take the samples from our fitted model. So every time we fit a model, we get this thing that Bayesians like to call traces, and it's just a jargon term for your samples from your MCMC. And that contains your posterior distributions, the thing you're interested in, the thing from which all your inference comes. I'm going to use those in a new model. So I'm going to notice I created a new model here called forecast model. And I'm going to give the parameters placeholders, dummies. Notice these are flat. Flat is a uniform from negative to positive infinity prior. And the reason I did that is it's not going to matter, because I'm not going to use them. I'm going to use the sigmas and rhos from the other model, because I'm going to use the trace from that. Okay? And then, so here, I pull out the, here's what I'm doing. I'm taking the last 2 fitted values, because this is an AR2 model, and I'm going to project forward from it.
This is a building announcement.
Oh yeah, we're having a fire alarm.
The fire alarm system is about to be tested. No action is required. This is a building announcement.
Any questions while the fire alarm's going off?
No action is required. This is a building announcement. The fire alarm system.
Okay, it's over. Sorry, they told me about that and I forgot about it. Okay, so then what I'm going to do, the way that we create a constant in PyMC is to use this thing called Dirac delta. So a Dirac is just a point mass on a particular value. And I'm going to do that on the last two values. So I'm going to fix those. And then I run an AR on that. So this is the same AR as before. Transform it, log normal. Notice I have no observations this time in my likelihood. The reason is I'm not even going to sample from, I'm not doing MCMC sampling, I'm doing posterior predictive sampling because I'm using the values I've already fitted to project forward. So I've got this little kind of dummy model that's just for forecasting. And it works. Wait, there you go. And it works. Okay, and it looks the same, except the dimensions are different. There's no data. And sample posterior predictive is what we do. So that, again, sample posterior predictive is just a simulator. We should call it simulate instead. Okay, and we get that, which is pretty cool. So it's a little bit dampened relative to the random walk. Like if you, this is just a prior model, this is no data with fixed AR2 parameters.
Attention please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts. Attention please. This is an emergency. This part of the building is being evacuated. Please leave the building immediately by the nearest exit. Do not use the lifts.
Okay, so even though the two models, random walk and AR, generate the same kind of estimates, their predictions are quite different, right? The AR2, that second lag dampens things a little bit, particularly here because there's it's a negative correlation, right? So it pulls things back down again. So we're less likely to be overrun with ground squirrels in the future. Okay? And the cool thing is, let's look at the test data. Let's look at what actually happened between 2000.
This is a building announcement. Testing of the fire alarm is now complete. Please respond to any further alarms. This is a building announcement. Testing of the fire alarm is now complete. Please respond to any further alarms.
It's a very important part of the test, actually. Not so good. Things didn't go well for the ground squirrels after 2000. They essentially collapsed and have stayed collapsed ever since. The ecologists call it a predator pit. So the hares collapsed, and then the lynx had to switch target prey and started hitting the ground squirrels, which were less capable of dealing with it and recovering. And so, yeah, no more ground squirrels. I mean, they're still there, but they're very, very low densities. In fact, it was a 0 in 2009. So these are, again, crappy models, right? The one thing they assume is that this whole AR thing is going to continue into the future, this stationary thing. The world isn't always stationary. So you got to be aware of what else is happening. So if I had hair data, I could do a vector autoregressive model that's beyond the scope of this. And I could have correlated it to the hair, or even better, the lynx data. And then maybe I would have been able to predict this better. Okay? All right. We have half an hour to do the advanced stuff, which is good, I think. Any questions on any of that? Particularly the PyMC stuff, if you don't understand it or have a clarifying question. Yes, sir. Other sources of data? So the question was, this is a really simple time series. The disclaimer is this was an introductory course, so I'm going to start with that. I hope this will be a little bit more interesting, hopefully. The question was, if you've got other things that aren't necessarily time series data, is it easy to integrate it into this type of an analysis? Was that your question? Categorical, yeah. Yeah, you can, and you'll see in the next piece where you kind of have these additive models, and you can have, you know, coefficients. They could be helpful for things like, you know, the predator pit thing here. If you had external data that wasn't part of the time series but informative, how do you do that? And Bayes is really good at that, because you can build what are called hierarchical models that have data that are measured in different places at different scales even sometimes, and you can bring those to bear. So you can, you know, like your regression model had a mu before. Well, you know, you could have made that mu a distribution that varies from place to place or group to group, categories, things like that. So it's easy to generalize these models and make them more complicated. All right, here's what I'll call advanced models. It's not super advanced. It probably should be more intermediate. I'm going to talk basically about two types of things: a generative model, and then I'm going to talk about a Gaussian process model, which is more exclusively Bayesian. So this is all about capturing some of these more complex patterns. These AR2 and random walk, these are just distributions, really, as far as PyMC is concerned. They're not models really in and of themselves. They're just components of the model that you would want to build upon to make something more interesting and realistic. So I'm going to go back to the births model here and try to do a better job of modeling that, not just throw a regression at it. And so we can look at a whole bunch of features of this data set and incorporate components of that into a larger model. So we have a whole bunch of interesting patterns here. Right, so we have the periodicity and we have the trend. We've seen that already. There's a day a week effect, right? There are fewer babies born on weekends because these days births are often scheduled, you know, either cesarean sections or induced labor, things like that. I've got 3 kids. 2 of them were born during the week. I don't know if that's informative or not. 2 of them were twins, so that's also a thing. But so again, I'm going to start off and then there are a bunch of other things: monthly patterns, holidays. You know, very few kids born on Halloween, lots of kids born on Valentine's Day. I don't know. That was what motivated this analysis in the first place, was some blog post about kids aren't born on Halloween, and Andrew Gelman is a very curious guy, and he said, is that really true? And found a data set, and here it is. So let's start with a stupidly simple model and build upon it, like I said. So linear trend model. This is even a sillier model than my polynomial one, right? Because this is just going to be a linear model. And we're going to start building pieces that soak up different components of this and then put them all together. And you can do this additively. You can do it multiplicatively, depending on what makes sense. All right, so here's our super simple starting model, right? Nothing should be surprising here, except I'm calling it alpha and beta now for some reason, but it's the same. And so this is the prior predictive check. So I'm making sure that my standard deviations, so I chose, what I choose? Just standard normals, standard normal, standard half normal, nothing fancy. And this is what it gave. And so you'd be looking for, you know, the data falls within where the prior kind of varies around, which we like to see that. If it's bigger, that's fine too. What you'd worry about is if, you know, the blue stuff was up here and not down here. It's not necessarily a deal breaker, but you're not doing yourself any favors. You're being antagonistic, and not really, you're injecting prior information that's just not true. So that's a good prior predictive check. So let's sample it. We'll simultaneously sample and do posterior predictive checking. Notice this model worked really well. No errors. We should do proper checks, but some of them have been done on our behalf, and we're not getting warnings. So, okay, and that's what the predictions look like. And so I've included the 95% HDI. We can call this an HDI or a probability interval or a credible interval. Frequentists have confidence intervals. We have credible intervals. And so you can see that all of that other variation that's not linear is just soaked up by the noise, right? What else is it going to do? So let's deal with the seasonality, or the periodicity, I should say. And what we're going to do here is a Fourier series. So this is a very common approach. All we do is we generate artificially a bunch of sines and cosines and add them up and weight them. So notice they have weights, and they also have periods. And this is going to be an annual seasonality, for example, for births, because we saw that pattern, more in the summer than in the winter, for example. And let's have a look at what these features look like, right? And so they're out of phase because they're sine and cosine. And then we have increasingly dense ones, increasingly lower period. And so I'm going to use 3 orders. And if you sum all those up, you get this. And actually, you know what? I'm going to run some of these models further down, take a while to run. So I'm going to run everything below, just so we're not waiting around, right? So you get these simple sine and cosine, then you get very subtle, interesting shapes when you add them together. And these are just flat out adding them together, like with no coefficients. So you change the coefficients and they can do weird things. That's what we're looking for, is weird things. Okay, and so we can add this to our model. So here's our coefficients from before. That's nothing new. That's the trend component. Here's the seasonality. So I have a bunch of betas, coefficients, and my dims here are Fourier features. And I think I made 10 of them. 10 in each set, each order. All right, and then I do just treat that as a regression, and then I just sum them together. So I'm doing an additive one here. I could also have done a multiplicative one. This also works. 1 plus that. So that would be a multiplicative model that's even more flexible. But I think for this one, additive is probably plenty good. Oh, I'm not running that again. I'm not going to run anything anymore. Okay, and then prior predictive samples also look good, not surprising. The sampler went without any error or warning. All right, so now we have a trend, and now we've soaked up a little bit of the periodicity, not everything, right? The problem here is there are multiple, so I talked earlier about seasonality and then periodicity, other oscillations. So there's non-annual, this is just the annual variation, right? So it's still a terrible model, I'm not gonna lie, but it's less terrible than before. And this is what the seasonality component looks like, which looks just like the one we'd pulled out using standard methods before, except it has confidence intervals around it. We know how certain we are about this seasonality if we got it wrong. Okay, so now we're going to add additional things. So there's within year variation, and then I also mentioned these day of week patterns, right? Doctor's not going to come in and deliver a baby on the 4th of July. So we got to model that if we're modeling things at the day level like we are here. Okay, so I'm going to jump ahead a few steps because we've only got 15 minutes left and build a more comprehensive one here. Okay, so annual seasonality, which we had before, we're going to do 6 month, we're going to do a weekly, we're going to do multi-year, so this is a couple decades, decadal cycle, excuse me, and then holiday effects. And so these are, you're talking about categorical information. This is kind of that, right? Holidays, these are just arbitrary days in the calendar that where people happen not to be working very much, at least in the United States. So 64 total features now. All right, so this is, so the model starts to look a little more complicated here. Although some of it is just a bunch of bookkeeping, I'm breaking up the Fourier features into these different components just for plotting capabilities. And then, so I have a total seasonality that sums them all up again. Holiday effects, and I have a certain number of holiday features. And so now all I've done, is I'm just expanding this slowly. Okay, and oops, I'm not sure what, there's a mistake there. Dang it. I think I forgot to back transform it. This part looks good though. So this is the, our enhanced model versus observed. So it's hitting kind of the periodic stuff pretty well. This green line doesn't actually look like that. I think it's been improperly transformed back. And so the residuals also is starting. You can still see some periodicity. I can't believe we still have residual periodicity, but we do. Yes, sir. Do you have to describe them in advance, did you say? I did hear, but that's a great question. So if you're a Bayesian, you sort of don't care. Like if you don't know how do you not know what the holidays are? But you could, what you could have is uncertainty around them and estimate them, right? So you could estimate day effects and make them day specific and allow the data to kind of shrink them to zero, if there is no actual holiday, Tuesday, February the 2nd or something like that. And then the 4th of July there would be a difference in the model between predicted and actual, and so it would soak that up with that day effect. So yeah, you could estimate day effects. Yeah, good question, yeah. No, they don't have to be fixed, but it makes your life easier if you know, obviously, if you know what they are. So yeah, you can see here, so this is Christmas and New Year's, boom and boom. But then also, what is this? December 19th or something? Is that the start of Hanukkah, maybe? Yeah, but there are other days too that aren't holidays that for some reason are low. There's 4th of July. It's not quite as low as you think. Doctors do come in. Okay, and then, weekly pattern. We hit the weekly pattern pretty well. These are estimates now, by the way. Another way, so I showed you forecasting before using a dummy model. You don't always have to do that. What you can do instead is include your data in your model. And what I mean by that is we built this model that created the graph that I plotted before that has nodes, which are your variables, and then the edges relate hyperparameters to parameters and parameters to likelihoods and so forth. Well, you can add data into that and make it a node in your graph. And the cool thing about the graph is that it's just it's like a series of tubes, right? It's just, you can swap things in and out. The values can change. And so what we can do is put data nodes, fit the model with some data, pull them out, put your test data in, and simulate with them. So then you're using your fitted parameters with new data. And that's what we're going to do. So now we have these data objects, and these are mutable. So we fit the model, and then we fit it up here, and then with our enhanced model, we use set data. And so up above, I had split this into train test. I've lopped off the last few years, and so now I'm putting in the test data for the Fourier features, for the holidays and everything. And then again, we're not fitting anything here. We're not doing any MCMC. We're just simulating. So now we'll generate forecasts. Hey, right? So green is our forecast. And if I go back and run this again, I'll get a slightly different green thing. This is just one trajectory, okay? So there's nothing fundamental about this dip here. The next time I do it, it could have gone up. So this is just one series. And then the forecast errors, yeah, so these are all the start of my test set is there. So it does pretty well for a couple of years, and then it, predicting the future is hard, right? Okay, yes, sir.
One question on the data amount, because you said you have like 64 parameters in that model or so, and I think it's 18, 20 years of data.
Mm-hmm.
So for each 4th of July, you only have 18 to 20 observations. Obviously you have already the feature just for the 4th of July.
Yeah.
So how can you assess if you still have enough data to actually make the model valid?
I don't think it would affect validity. It would just affect the precision. Yeah, so it depends on how variable holiday effects are, right? If some Christmases there are a lot of babies and some there aren't, most there aren't, then you'll have an imprecise estimate. Or it's just naturally variable, right? There is no fixed. We're modeling it as a fixed effect, but it's different every year. Some years it's big and some years it's small. So yeah, if we had 100, well, for one thing, if you have had more years, things were different 100 years ago. We weren't doing cesarean sections and stuff. So so the system is changing, and therefore that's really not more data. It's data for something different. So yeah, it shouldn't affect the validity of the model. It should just affect your precision.
Where do you draw the line? Where you basically say, okay, I have too little data to actually include those 64 parameters. I have to cut down.
Right, yeah, so you can do formal model comparison. So we have a metric called WAIC, which is an information theoretic measure of entropy, and so it compares model fit from one model to the other. So you could do it with and without holiday effects, and if it's better, you can retain them. It means it's got some predictive, it's an estimate of out of sample prediction power. And so if it doesn't improve that, then maybe you leave it out. Yeah, or leave one out, cross-validation, which you can do here as well. So you could use it that way. But sometimes you just want parameters in the model, and you don't necessarily want the lowest criterion. We're interested in holiday effects, so let's put them in, and we'll live with it. All right, only 10 minutes left. I'm not going to do a very good treatment of Gaussian processes, except I'm going to do kind of a first pass, and then we'll stop after sort of 5 minutes or so, and I can answer questions. Because this is just the next piece. Like I said, on YouTube, there's a PyData New York from last year where we did a whole 90 minutes just on GPs, right? So GPs are fundamentally non-parametric Bayesian method, very flexible. It's non-parametric in the sense that it's got infinite parameters. So the name, again, makes no sense. What we do is we take a multivariate normal and we generalize it to be of infinite length. And so, as a computer scientist, if you've got a vector and you want to make an infinitely long vector, what would you do? You'd probably write a function instead, right? You can't store infinite, and so you'd write a function to return whatever elements of that vector that somebody wants. And so this is the case here. So remember, so if you recall, if you're familiar, this is a multivariate normal, and it's got a mean vector and a covariance function. We're going to generalize that to have a Gaussian process that has a mean function and a covariance function. So if you take a draw from a mean function, you get a mean vector. And if you take a draw from a covariance function, you get a covariance matrix. So finite instances of the GP is just going to be a multivariate normal. And the cool thing about it is that depending on how you choose this, so the covariance function essentially determines how autocorrelated samples close and far apart are. So this is a squared exponential one that has kind of a rapidly declining, things become independent as they get further and further away. You can get ones that are, so a draw from a GP kind of looks like this, right? So a realization from a GP is a function. And so rather than estimate coefficients for regression parameters and things like that, we're directly estimating the function because every draw from a GP is a function, right? And so depending on how you choose this covariance parameter or function, you'll get different types of lines that can be, you can get even do periodic ones, like so. And so the way that it works is that, the reason that we use a multivariate normal for this is that it's very easy to integrate out the points in this infinite function that you don't need. Because you can marginalize normals really easily, and you can condition multivariate normals really, really easily. And so we can use that to model these same time series. So let's look at this guy. So this is just some simulated data. The true value, the true data is the blue line, and the points are the data that are simulated from it. And so we're trying to recover that blue line. And so I'm going to do that in PyMC. Here we go. I'm going to choose a Matern covariance function, which is similar to this guy. Just creates wiggly lines. And did I zip past it? There we go. There we go. The mean function tends not to matter very much. I'm just going to pick a constant in this case. All of the learning comes from the covariance function. And so here's a GP. So there are a couple of different kinds of GPs. There's a marginal and a latent. If you're modeling data directly, you use a marginal. If you're trying to model a latent function like we were doing with the squirrel densities, you'd use a latent. So we're going to model this data directly. So this is going to be a marginal, and all we do is specify a mean function and a covariance function. And the length scale will determine how wiggly these lines are going to be. So a shorter length scale means there's more variation from point to point. Long length scales smooth things out. So we put, they're unknown, so we put distributions on them. So these are the things we're trying to estimate here, are these hyperparameters. Okay? And so very similarly, rather than a regular likelihood, we have a marginal likelihood. And the only difference is we've got to pass x's as well as y's. So we've got to pass at the points that we're interested in dealing with, because again, this is an infinite line. So when we're passing it the data, we've got to pass it the x's as well as the y's. And we do MCMC sampling as before. And then we can predict. So we can use the conditional posterior of the Gaussian process. But again, the way that we do it is slightly different. So we're going to open up our model after we fit it and use gp.conditional on some new points. So this is just a linear space from 0 to 20. I'm going to try to recreate the line, essentially. 600 points. And so I'm going to condition on those points rather than the data points. Do posterior predictive sampling. Okay, and so we get, there's the true blue line, and then each of the red lines is a sample from the posterior GP. And then we have also projected out into the future. And so it's going to follow that same GP. One of the things that it does is that it kind of retreats to the prior mean function, which is why it's dropped down here to 1. I think I specified it as 1. But you can see it does a really good job of kind of characterizing the variability. I'm going to stop here, other than to say that, again, this is just kind of a starting point. The rest of it is mostly about faster GPs and incorporating them into the model. Let me just zip to the end here. There's There's way more. Again, this is introductory time series. If I were to do advanced time series, I would include some of this other stuff. So specifically, Jesse Grabowski, who's one of our core developers, has developed state space models, which currently resides in the PyMC extras package. It's kind of a bunch of add-ons that we have that aren't part of the core package at the moment, that does a whole bunch of structural time series modeling, Kalman filtering, more advanced things like that. You can do vector autoregressive models that I mentioned before, Bayesian ones. We've got a tutorial on that on our website. There's a lot of resources on the PyMC website related to time series. One of our Google Summer of Code students from a couple years ago did multi-output GPs. So rather than one time series with GPs, you have many that are related to one another. And then great places to continue the journey here. Again, the PyMC examples. Stan's user guide and forum are extremely good. We steal a lot of things from the Stan project. Our discourse forum is very active. Please come along and ask questions there and answer questions too. And our GitHub discussions, of course. Lots of other PyMC extensions like Bayesian Bayesian additive regression trees can be used for this kind of stuff as well. Bambi, a higher level package. And then finally, again, if any of you came in late, we're doing a code sprint tomorrow for a couple of hours in the library. I'll be there, maybe a couple of other PyMC developers too. And you can come in and talk more about this stuff, or you can hack on some code, write some documentation, squash some bugs with us, and learn a little bit more about how the PyMC API that I breezed through today works. So thanks everyone, thanks for coming, and enjoy the rest of the conference.